Mejor, ¿no? Voy a ponerlo aquí ¿No?
Me dijeron que da preferencia.
Ah,
No sé por qué.
ok. Impresionante. Maybe I will do English. Okay.
The,
You can speak Spanish if you want, but maybe I will do
Uh,
English maybe.
the Good evening, everyone. Let's go to start more one PDE seminar today with Professor Emeric Bouin. It's a real pleasure to that he be here, and he will talk to us rates of acceleration, local reaction, diffusion, dispersion models from biology.
Yeah, thank you very much. Thank you for this invitation. Maybe I will do the talk in English because it's a bit easier for me. I could do Spanish, but since I'm not so well prepared, I will do English today. Yeah, so I'm going to actually present a kind of overview of some results I've obtained recently and not so recently with various colleagues. So Jérôme Coville from Avignon, that he visited Chile a while ago and actually has some roots here. Jimmy Garnier from Chambéry, Chris Anderson now in Arizona, Guillaume Legendre from Dauphine, Florian Patou now in Avignon also, and Lenia Rigic from Stanford. So the talk is about rates of acceleration. So I will explain exactly what it's really in the very soon future, in some reaction diffusion models that are inspired from biology. So maybe before I will give you a bit of context, okay, and show you some Mickey Mouse pictures. So basically the kind of problems I'm interested in is to follow the dynamics of invasion of some species in some land, okay? So typically, imagine we are looking at South America, so we are here at the moment. This bee is actually a very aggressive bee. Can I share my screen? How can I do that? What should I do? You want my... you want me to go on Zoom? Aha, okay. Where did you send me the link? Email?
I will send you.
Okay. Email. Let's do it. Or you want me to send you, I can send you my PDF if you want, if it's easier. Yes? What should I do? Okay. I put here because then I know where it is. Is that me doing that? No. Okay. Yeah. I think I'm here, no? Now what should I put audio also, or what should I do? Share my this one. Okay, but maybe I should not put sound, no? Or what should I do? Is that fine now?
Yeah.
But maybe I will turn off the sound. Okay. Vous n'entendez rien. Non, mais c'est normal. Okay, fine. I don't know if I can pull full screen now. It should put like this, no? Okay, so imagine this bee here, very aggressive bee. okay, that doesn't have so many predators, okay, and is really able to attack a lot of things. So clearly, its invasion is not really, let's say, constrained. So it can invade a lot. So you see that we can, if we follow these level lines, B is kind of like diffusing nicely in the land. So of course there is some heterogeneity in the landscape. So sometimes it's a bit slowed down, but if not, you see that the invasion is kind of homogeneous and progresses nicely, right? Another example. So yeah, keep in mind that I'm really interested in understanding the dynamics of this kind of interface. Another example. So you take this, what is this? Sorry, we put this out. So another example, you see the leaves of this plant, okay? And we inject a kind of a virus in this plant, and the virus is highlighted by some kind of special chemical that makes the plant being kind of fluo with it. And you see, even though it started from here, then after some time, since it can, is where it can diffuse very much faster, you have a bit of virus here, but you also have virus much farther at the same time, okay? Which was not really the case with the bee, because the bee started, oops. Yeah. What's wrong here? Okay. The bee started here, and the level lines are kind of chronological, right? So this is a river in France, okay? And there is this poplar rust that has been invading a lot here. And since it can follow the river, it can use the river to spread out much faster, right? So basically, initially we had a bit of people here, then a lot here. But you see that you can also have some spots of this invading rust much farther from the origin. So in a sense, in this kind of invasions, the thing is non-local. Since for the bee started from the initial point and was like invading like this. From these cases, it's a bit more okay. From the initial point, you can have some large jumps due to environment or due to the way that the species is invading. Okay. I don't. Here. Another example of invasion is given by this, what's called in English chemotaxis, which is a movement of clusters of bacteria. So imagine, see this experiment, you put a cluster of bacteria here, okay, and you want to know how much they are able to invade. This is a channel, go inside the channel. And actually, so bacteria, when they are in a cluster, they're able to communicate by a chemical signal to stay together. And they all eat the sugar in the channel, okay? And what we realize, in fact, this experiment shows that all the bacteria will stay in a cluster, and this cluster will move with a constant speed, okay? So we can track the trajectories and observe it with, this is experiments from people from Institut Curie in Paris. And they're able to see a local trajectory here that we'll comment on just afterwards. And globally, the cluster is able to travel at some constant speed, okay? However, during the movement, during the traveling time, some biologists have realized that, in fact, all these swimming bacteria here that you could see here are, in fact, doing microscopically a movement that is more Levy walk, let's say something with very large jumps, more than a Brownian thing. Saying that basically their movement, you can see the sentences here, basically we find that the bacteria are performing super diffusion consistent with Levy walks. Okay, so basically the tails of their movement is more an algebraic thing than a Brownian. Okay, so what I will be interested in is to see, okay, can we show some models where we can describe this kind of invasion at constant speed with local movement or non-local movement, or et cetera, et cetera. And the last feature that I want to discuss is exactly the feature of my title, which is acceleration movement. So let me present my very nice friend here. So if you shake hands, so it's to you. So this is in English cane toad. So it's a very aggressive toad. You can see on the skin it has some kind of spots there, and this is poison. So basically, so this toad has been introduced in Australia around 1940 or something like this to eat a pest in some crops. Okay, but actually they do very aggressive and decided not to eat the pest and just to go away and live its life. Okay, so basically, as for the bee, this guy has no predator because, for example, if a crocodile eats the toad, it dies because the toad has some poison in the skin. So it's very aggressive, and basically it could enjoy some free motion along the line of Australia. Okay, here it's a desert, so it's too arid, so there is no water, so the toad cannot survive. Nevertheless, it can travel all along here. The special interesting feature is the following thing. So when it has been introduced here at the beginning, the speed of invasion was more or less 10 kilometers per year. Okay, and in fact, they realized that now at the edge of where they are, the fastest toads are going at 50 meters per year. So basically, their main speed has been multiplied by 5 in 80 years. Okay, so this is exactly consistent with an accelerated expansion because for example, it's an accelerated not as for the bacteria that were traveling with a cluster with finite speed. Okay, so actually, of course, if I decide to walk all along Australia and have as many kids as I want, they are not going to go five times faster, right? So there is really some explicit strange things that happens for this invasion, and this is what biologists called spatial sorting, which is as much as the toad invade, the faster toads are always at the edge of it, and when they have kids, they transmit their trait to their offspring, and thanks to the mutation, the kids have a possibility to go faster even. Okay, and since there is no toads at the before the edge, the faster have an advantage because they can eat food before the others. Okay, so as much as they go, they go faster, and their legs are stronger, let's say. Okay, voila. And so this is more or less the aim of my talk, is to show you some models that describe finite speed, accelerated speed expansion with local or non-local movements. Okay, so a quick comment. So there's been some data collected by biologists, and you see, for example, on this section of Australia. So the data, they had it very nicely. So of course, recently they do GPS belts, but in 1930s we didn't have GPS belts. So they just, for example, kids, when they saw a toad, they would send a postcard to some scientists. Okay, and because it's been a real thing there. There's been some movies, there's been a lot of things about these toads because they kill everything and they are very toxic. So it's been a very interesting. Like if you see a toad, you don't have to touch it, you don't kill it, you have to like put it in a bag and etc. It's been a very big thing. And the data are consistent with an expansion that is not, the position is like a constant time times the time, which would be finite speed, but more, so this is finite speed, but more x is like a constant times t to some exponent, which is roughly 1.63. So you see that if you are like this, your speed is, of course, increasing with time, because if you differentiate this, then you don't get a constant speed. Okay. So yeah, so after this is this picturing introduction, let me tell you exactly what we aim at doing in this presentation. So we have seen invasion at constant and accelerated speed, okay, that happen in nature and real life, and that the dispersal processes may include like small jumps, okay, or eventually non-local and large jump possibilities, okay. So one part of my work has been to study qualitatively and quantitatively. So qualitatively is saying, okay, the profile of invasions look like this. Is like, okay, it goes at this speed with this exponent, and we can provide some explicit computations and stuff like that. Okay, and since this is what has been very difficult historically, there is an accent on non-local models for which the mathematics are usually a bit more hard. Okay. I will try, depending on time, to show you 3 types of models. So the first thing is the model for these cane toads. Okay. Second thing is, which is more for this poplar rust that moves with doing some kind of jumps. Okay. And then, if I have time, another type of models where we take into account a bit more biological phenomena. Okay. Okay, so let's go in the direction of presenting results about the cane toad invasion in Australia. So actually, all of these models are more or less related to the most basic model that has been introduced in mathematical biology to describe invasions, which is the Fisher-KPP equation. So initially, so in 1937, there's been a work by Fisher to describe the evolution of genes in some population, okay? Taking into account mutations and reproduction of species, okay? So basically, the idea was to try to see if it's possible to see a wave in the phenotypes. That is, you have a phenotype, you have mutation and reproduction. Can you have an evolution of the distribution of phenotypes in the population? Okay. So let me just explain what it is. So actually, it's starting from very basic principles. You say, okay, you take a population. It is able to move with very no biased small jumps. So this is assimilated to a Laplacian diffusion, okay? And as far as reproduction is concerned, if you don't have any, let's say, competition, if you're just alone and you can enjoy food as you want, then you have an exponential rate of reproduction, okay? However, since in the habitat you have a limited amount of resources, if there are too many people at the same place, then there are a bit of competition for food. So basically, if there are too many people, then there's no food for everyone, so people will start dying. Okay, so basically that's why you have this rate of death, which is if U is too large, then your rate of death will be large, and then will be larger than your rate of birth. Okay, so you get this very simple, that maybe I will keep here, very simple equation in the literature, which is a reaction. This is diffusion. This is diffusion, and reaction. This is a reaction term. Okay, diffusion, reaction. Okay, and so here people do small jumps, clearly. And actually, so the most interesting thing for this model that has been derived a bit independently, but around the same years by Fisher and KPP. KPP is for Kolmogorov, Petrovsky, Piskunov, which is if you take this equation and you start with an initial data that is, for example, concentrated on R minus, okay? Then this data, this thing, the population will invade the positive values of X, at a finite speed of propagation. And there is what's called a traveling wave solution, which is a black one. Traveling wave solution, which is basically a profile, which is like this, that is able to travel with this finite speed. Okay. So clearly, a traveling wave solution is something that can model an invasion, okay, at finite speed. So the exact theorem is that there exists a minimal speed C star, okay? So R should be here and theta should be there. Sorry, I forgot them. Such that for any speeds greater than this C star, there exists a traveling wave solution that goes at that speed, okay? So more or less, the most important thing is to know how you get this speed C and why your traveling wave is going to attract any solution, because this is exactly what this theorem says. If you start with a compactly supported initial data, then your n will propagate with the minimal speed, and your solution, the shape of it, will resemble this traveling wave. Okay. So let me comment, because this is only for this is only giving you finite speed propagation, right? So let me comment, can you get acceleration for this KPP? Could you get that? So let's investigate. So actually, the first thing is that if you take U0, so I said for the previous slide, I said that U0 should be compactly supported. In fact, you can relax this assumption by saying, okay, if your U0 is decaying sufficiently fast as an exponential with a rate that is large enough, then you will also spread with this minimal speed. Okay. So now we can wonder what happens for lambda smaller. So let's see. In fact, the result is if you take a reasonably decaying thing, but enough, then your speed will be a function of this rate lambda. Okay. So it's a function, if I draw it, it's an easy function. It's a function that is like that. Because roughly, if lambda is small, you're like R over lambda, and if lambda is large, you're linear. So it's something like this. So you see that if I play a little bit, and I'm taking a lambda that goes to 0, this is flatter and flatter, my speed is going to go to tend to infinity. So this suggests that if I take a decay that is slower than exponential, for example, a polynomial initial data, then there will be acceleration. And this is a result, oops, this is a result actually by Hamel and Rock from 2010. The problem with this is that actually it plays with initial data. And this is not exactly what I've told you at the beginning, because I was saying, okay, the toads were put at one spot and not everywhere. Okay, and for example, for the cluster of bacteria, they are put at one edge of the thing. So this is not really consistent with what I want. Okay. So now let me show you a model that is inspired by that, but is not exactly this, but can have all the features that I was talking about. Okay. So I will present you a model that is non-local. Okay, that is a reaction diffusion model, but that also takes into mutation, genetical mutations. Okay. And that is supposed to model the invasion of these cane toads populations. Okay, the big thing to get to keep in mind is that actually the propagation of the species is very much influenced that of length or motility. So because as I told you, the biologists saw that the faster are always at the edge. So there is really something heterogeneous in terms of the way that the population presents the edge. Okay. So since this heterogeneity is very much important, we will keep in mind this motility, this variable of length of legs, for example, to speak fast. We'll keep it in mind as a variable. Okay. So in this model, we have time Okay, we have X in a line, for example. So let's say that the coast of Australia is linear in a sense because they cannot really invade the middle, so they follow. So let's say that it's a 1D thing. Okay, to simplify the discussion. And actually now we keep track of this variable theta. Okay, that is of course subjected to mutation, genetical mutation, because when a toad has offsprings, then it will transmit these traits, but with a small modification. Okay, so the model reads as follows. So your ability to disperse in space, so to move in space, is given by, let's say, if I say quickly, the length of your legs. So the longer they are, okay, the higher is your diffusion. So now I add also genetical mutations that are a little small change in this variable theta, okay, and this is assimilated to a diffusion in this variable. Okay, so now I get a new operator like this. And as far as reproduction is concerned, so I have, of course, my free growth rate population, but now the competition for resources is actually independent of the length of your legs. Okay, so when you are at one spot, you're competing around, okay, at that spot. The way that the toads eat food does not depend on the legs, because when they eat, they are just not moving. So it means that this death rate is actually the integral of the density at that spot on the variable theta. So as I told you, this is a reaction diffusion mutation model, because there is diffusion here, there is mutation here, and it's non-local because I have competition that is an integral. Okay, so this looks like to take into account kind of a lot of biological things. So where does this theta live? It lives in an interval. Okay, so let's say that this interval is contained in 0 open, because you cannot have legs of length 0. Okay, so and actually the will be either finite or infinite. We can, since we want to see some transition behavior and etc., we'll see that in fact this has a bit of influence. So the crucial difference with the standard KPP that I showed you earlier, this one, is that this guy has no comparison principles or stuff like that, because it's there is a non-locality here that kills all this kind of structure and makes the math a bit harder. So let me explain. So the results we obtained, so we had a first result here, which is, okay, let's assume that the available traits are in a bounded set. Then there exists a positive constant such that we can follow the level lines of at least this height, saying that, okay, we know that then if I start with localized initial data as here, then it's going to invade the space with finite speed. Okay, so basically, if I put my finger on the place, for example, where the density has this value, let's say it's 1/2, okay, whatever, then I know that this point is moving like C star T minus some correction. Okay, I will not detail today this logarithmic thing, but in any case, in this bounded framework, then we can show, in fact, that things are moving at finite speed, and this is also another result, that in fact at the edge of the front we have all the toads that we have in majority, let's say, toads with the longest legs as possible. Okay. So actually, this is not really fitting the data of the biologists that had this thing, right? So to get that, let's release the boundary. Let's say, okay, we take theta can be arbitrarily large as possible, and we see the dynamics. So we have two results. The first result is like a first step, okay, to understand what happens. To understand what happens, we go to a situation where actually the math are easier because there is a comparison principle to check what happens, which is we replace the row by the standard n. Okay. Situation, okay, it's much simpler in terms of this, but what is difficult is to get the Sharpe rate already. So what we've been proving is that, okay, if I put my finger at one spot, this spot will move at a constant times t to 3/2. Okay, so this is consistent with an acceleration. Of course, not exactly the same exponent, but okay, curiously, their thing was 1.63 plus minus 0.13, so it's roughly okay, it's close, but anyway. Yeah, so when we release the boundary, it's possible to show that this equation admits an acceleration phenomenon. Okay, so let me just explain a little bit of how we do that, because it's a bit standard. So let me explain. So basically, the philosophy here is to follow the trajectory that has taken a toad that at time t is at the edge of the font that I'm looking at. So this looks like a kind of Lagrangian trajectory, an optimal Lagrangian trajectory for something. Okay, so the idea is to try to find these relevant trajectories in some kind of natural scaling. Okay, so in fact, what you have to do, so here you have to trust me in a sense, is to take the referential framework that fits with the acceleration that you want to see. So if you scale t as epsilon, since we expect that x and t scale x is t 3/2, then we'll scale x as epsilon 3/2, right? And then by homogeneity, in fact, it turns out that you have to scale theta as theta over epsilon. If you do that, and this is actually more or less the only relevant thing to do, you get, for the linearized equation, you get something like this. That looks like a diffusion equation with some very small diffusivity. Okay, and then there for this there is a full theory that I don't have time to detail exactly, but which is related to large deviations, that tells you what you have to do to study this kind of things in this scaling. What you have to do to find the Lagrangian trajectories is to do an optical transform. Okay, you change your W, so your solution, you change it as exponential of minus a phase over epsilon. Okay, so it's a bit like a WKB transform for people who know that, but it's still the real. So it's a bit more to study concentrations. And actually, from this diffusive operator, you will get a kind of Hamilton-Jacobi equation, okay, relevant, that will give you some trajectories. Because you know, if you have an Hamilton-Jacobi equation, there is a Lagrangian, an Hamiltonian, you have trajectories. So actually, for some reason, it is relevant to study this kind of Hamilton-Jacobi equation and to find the trajectories. So actually, for this model, you can make some computations. And luckily, but in fact, it's not necessary to be explicit, but luckily in this model, so for that talk, it's nice to see. There is an expression of the limiting phase, solution to that, and the Lagrangian trajectories, that optimal trajectories associated to this energy. Okay. So why it is interesting to keep that in mind and to use it, it is because then, if I manage to pass to the next, oops, it's been jumping too much. Let's say, okay. Because from these two informations, no, toujours pas. Voilà. From these two informations, I can do two things. So actually, and this is kind of a, let's say, it's a strategy, it's a technique, it's a, if you want to know at which speed something moves, what? Ah, the black, sorry. If you want to see at which speed something moves, you're going to do sandwich, right? You're going to construct something from below. Since you have a comparison principle, you're going to build something from below that moves with the scaling you want, and something from above that moves with the scaling you want. And it turns out that with this Lagrangian study, I can construct that. So somewhat miraculously, with the computations, we can get an explicit super solution using the phase that has the good spreading. And for the lower bound, we use the optimal trajectories to say, okay, I will take in the x theta a bump that move along the optimal trajectory and say, okay, the population is going at least at the speed of that bump. Okay. So this is it. You take an optimal Lagrangian trajectory given by this Hamilton-Jacobi equation. You slide a suitable bump, and then by a matter of Dirichlet eigenelements, you can show, in fact, that on that bump that is traveling on this trajectory, you have enough mass so that the bump will indeed push your solution and not just vanish at zero. Okay. So of course, the interesting point here is that I never prove the scaling limit. I just guess what it's supposed to give me as an information, and I use this to construct another object that is related, okay, which is much more constructible. It's just a bump that you slide. But if you don't slide on the good trajectory, you're going at the right speed. So. And actually, this is how we get the other result for the full non-local thing, for which there is no comparison. So we have to do some argument by contradiction, but still, we managed to prove that the edge point divided by this spreading is at least going at that. The constant is at least this, and at most that. Okay, so this C is between the two. And actually, this is not sharp, and the constant is between the two, and is not this one, and is not this one. But this has been, in fact, done later by other people, by, in fact, optimizing a bit more what we've been doing on the trajectories by taking into account the non-local thing. So it's been quite involved. Yes. Okay. Fine. So this model can indeed show acceleration. We can prove it theoretically, in fact. Actually, when we have been discussing with biologists in Australia, they were saying, there is something that is quite important in biology, which is if you put a lot of energy in reproduction, you cannot put as much energy in moving. It's kind of a trade-off between, well, it seems that this is a biological thing. So, okay, a biological important concept. So basically, if your legs are too long, you cannot put that much energy in reproduction. So basically, you will more die than grow. Okay, and actually, they were kind of interested in knowing if we could put this information in this kind of models and see what happens. So this is what we did later. So we take into account a penalization. Okay, we say if the trait is very large and too large, then it's a penalty on the reproduction rate. So it adds a mortality trade-off, saying so I have a function m saying, okay, if my trait is too large, then I will in fact more die. Okay. And the question is, okay, is it possible that in this situation, by saying, okay, m is an increasing function of theta, it goes, okay, say that we have too long legs, then the thing is really making a strong penalization. Can we still recover acceleration, or can we compute speeds? Okay. So we obtained the result with some Australian colleagues, Sean and Kim from Sydney, and Chris Anderson from Arizona, saying, okay, we have, let's say, a dichotomy and a dichotomy in the dichotomy. So let's denote by gamma infinity the normal eigenvalue of this operator. Okay. Basically, this eigenvalue is just saying whether or not the population can solve. Okay. So if this eigenvalue is negative, then it means that my M is too strong so that I kill everybody. Okay, so in this case, there is extinction and there is even no propagation and everything. Okay. However, it could happen that this eigenvalue is 50. Okay, so that there is invasion. But then if there is invasion, at which speed is this invasion going? Okay. So let's study this case. So if this eigenvalue is positive and we have propagation, actually there is two things happening. Either m of the limit of m over theta is positive, then okay, this m is strong, but not strong enough to kill everyone, but it's strong enough to solve the acceleration phenomena. Because the height rates are not reachable anymore. So it's a bit like if I was in the compact case setting, for which I had propagation at finite speed. But if you take m of theta that is going to infinity, but not too fast, then it's not killing enough the height rate, and you can still accelerate with a rate that we can explicitly compute. Okay, you have to invert a formula with this integral. So let me just show you some numerics. So actually, when there is no constraint, you see that the rate was t to 3/2 from above and below. Now our rate is eta of t to 3/2, but eta is solving inversing. So it's exactly t, it's a function of t. So let me show you some numerics. So I take m, so the most natural thing is to take theta to the p and adapt this exponent, okay, to c. So let's take m is theta to the p. So if p is 1/3 or p is 2/3, okay, you see that if p is now there smaller than 1, so I'm in the acceleration regime for my slide. And you see actually that, okay, so here it's not super obvious, but here, if I put my line here, in fact, it goes there. It's starting to, this is not exactly, they are not exactly aligned, these points. And actually, the spreading rate is 3/2 plus p. So, yeah. So, yeah, so this is x and this is theta. In fact, this acceleration process is really due to the fact that you're able to take arbitrarily potentially large things with some eventual ratio. And here, a linear regime, you see that if I take theta smaller, you see that here these points are really, this is really, okay. Fine. So let me just comment on how we did that, because then this model is a bit non-local. Okay, so and there is no comparison. So actually, we have been using something what's called Leo estimate for diffusion operators that tells you that you can derive a bound from above that looks like this. Okay, so it's exponential of a constant times t minus a zeta over 2, and you observe that this zeta coming from the Leo estimate has clearly the shape of some Lagrangian or formula, right? So this is not actually saying that this thing that looks like an Hamilton-Jacobi solution is a super solution. This is not true in general, but nevertheless, you can bound from above your solution with this data. Okay, so it's a bit a subtlety, because for the previous model, we were able to show that in fact this Hamilton-Jacobi Cook type solution was actually a super solution. So this is not always true in some particular and difficult cases, but even though you can bound from above still by this. Okay, and for the lower bound, in fact, we use still these moving ball techniques by contradiction arguments and finding some reasonable passes. So the difficulty when M is a bit general is that you cannot compute an explicit Lagrangian thing that is optimal. It's difficult. But nevertheless, we managed to find a path that is reasonable to the acceleration. So basically, the idea is the following. You need to have large traits to accelerate. But these large traits make your solution die like crazy because the M is too large. So what you do is, okay, you take your ball, you slide it to high traits, okay? You run by dying, and when you die too much, you come back to safe zone, okay? You regrow a bit. But since in this zone you grow basically exponentially fast, it doesn't take too much time compared to polynomial. And then you do it again. So it's a bit, you don't have the explicit thing, but you can still manage to. Fine. How much time do I have? Tell me. Okay, so I can present you some other models. Okay, super. Yeah. But okay, the point is that when you is actually what makes, in fact, so the dynamics of a KPP solution is like that. You have basically a part of the wave where you're close to 1, and a part of the wave there is nobody. And in fact, in this area, this U is very small. So here, your solution goes indeed almost exponentially. That's why, for example, at the edge here, when you have just sent a very, very few number of people and you come back to safe zone, you have at your disposal indeed very favorable. So yes, this is why in the KPP theory, these fronts are called pooled fronts because it is always individuals that are at the edge of it that are pulling everyone to the right by growing kind of expression. Okay. So now I want to focus a bit more on movements for which the jumps could be eventually large, because there, for the toads, I was discussing spatial movement that is roughly like microscopically Brownian, that is, things are moving locally. So now I want more to illustrate stuff where you can have pretty large jumps when things move. So actually, this is more done by so-called integral differential equations. Okay, but actually they are related to KPP type equations. So usually they are in the same area, let's say, of mass. Okay, so let's start with a very basic thing. I take almost the same KPP equation, but I replace the diffusion by a convolution operator. So let me just write briefly that is usually very much used to describe arbitrary large jumps, because operator where J is a density. Okay, it's something like this, very easily written like that. U of y minus U of x dy. Okay, so why is it representing some jumps? It's just saying that, okay, when you want to go from a position x to a position y and vice versa, the probability that you can do that is by the density. Okay, so now, for example, you can have a very fat tail thing. Like if you have high probability to go far, you can encode it. So this is called a dispersal kernel because it's telling you the probability to go at this distance. Okay, and since this J can eventually have fat tails, we could wonder what is the influence of these tails on speed of invasion. Okay, remember that for a basic KPP, I travel with finite speed. May I kill this phenomena or change it if I allow large jumps? This is the question, basically. Okay. So let me show you some simulations. Okay, very basic simulations. So, for example, if I take J is what's called thin-tailed. Thin-tailed in the KPP literature means basically that you decay faster than an exponential. So sometimes you can read in the literature there exists a lambda such that, so of course this is plus, this thing is finite. Okay, so that basically if you are like a Gaussian or there exists, so or some kind of an exponential, this integral will be finite, so you're thin-tailed. Okay. So for example, this simulation is for a Gaussian. You see that for a Gaussian, I start with it's just a very simple indicatrix of it. Then there is an expansion. It's yellow because of my screen, sorry. Let me just change that because it's a bit boring for people to see. Yes. Sorry about that. Okay. See that if I've replaced my J with a Gaussian, then I put my finger on the point where the solution has value 1/2, and you see that this thing is linear, right? So I have a finite speed propagation, and actually the front looks like a traveling wave invasion. Now I take a fat tail thing, but not too much fat tail, but still a bit fat tail. So for example, I take exponential. So this, maybe I do like that. This was, for example, this. This actually will be this. Okay, so it's fat tail because it's not exponential decay, but it's sub-exponential decay. So it's it. And you observe that even though I've started with a compactly exported data, I put my finger on the front, and that guy has an accelerating speed because this is not a line. Okay, so actually this thing is a polynomial spreading. It's a bit like that. And now if I take very fat tail, so usually very fat tail in the literature of that it's a polynomial. Then it goes like crazy because you see I start here and immediately this is spreading insanely fast, and actually this is an exponential. And as a side remark, doing these things numerically is kind of costly because if you want to observe something that propagates exponentially fast, you need to have very, very big truncations, or you need to follow your front with a moving box or something like that. And this is not easy to do, in fact. It looks very easy as a setting, but in fact, to have it precisely, it's costly. It's not easy. Okay, so this is just now a reminder of what I've just said. So if you take thin-tail data, meaning this integral is bounded, in fact, there is a kind of a literature that tells you that indeed you have invasion with fronts, like for KPP. So there is a lot of works, right, including by Jérôme, that actually did part of these works here, in fact, at some point with Salomé. And if you take fat tail things, there are a few works, but not that much. And actually, the first one is due to Jimmy Garnier. So my contribution here, is the following. So it's to provide, if I take a J that is in a sense quite general but fat tail. So basically, I'm reaching the boundary possible for fat tail, and I'm reaching the boundary possible for integrability because it's a probability density. So I cannot touch this 1 over x, but not too far. If I take a j like that and I follow the point where the solution has value 1/2, this point function. So I take minus log of j. Okay, so for example, minus log of j here, it's an easy minus log of j. It's an easy x 1/2, and here it's an alpha log. Okay. This point, so the invasion point is as the f-1 of this. Here it's more, it will be t squared, and there it will be an exponential, as I told you. Okay. So if j is like that, we get the exponential, and if j is like this, we get the polynomial, and it corresponds to the simulations. So in fact, the difficulty here is to get the sharp thing, because here I really have that this point is equivalent to that. So in the literature, people before add some, for example, bad constants here, or bad remainder here, things like this. Okay. And here the strategy was, and I want to just comment quickly on that because it explains the process. So in fact, when you have an acceleration phenomena, what happens is that, okay, and actually you can see it from the simulations. You see, if I manage to go, no, toujours pas. I managed to go back to the good slide. Yes. What you see is that it's pretty explicit on this simulation. The thing expands, but as much as it expands, it flattens. You see, it's getting flatter and flatter here. So this makes the thing very difficult because you don't have a profile of acceleration. It's not something that is translating with an accelerated speed. It's much something that expands, and while it expands, it flattens, and this is going to accelerate the process. So this makes things very difficult. And the way that this appears is actually that usually in this kind of processes, the growth and the diffusion are a bit decoupled, which is you start with a very concentrated. Your first step is to disperse everybody with this j. And actually, okay, you have to trust me on that, but when you do that, your completely supported function will look like time 1. So basically, after time 1, your solution looks like a multiple of j at the edge. Okay? So you're becoming a fat tail thing. And then from that, this j, basically, the movement is more or less taking just the logistic part and making the j grow. Okay. So this is what is said here. If you start with you take only the logistic part, you grow at each spot x, or according to starting with an initial data that looks like j. Your solution, in fact, roughly, and in this case, it's computable, but this is for the slide. Roughly looks like something that has a good rate. Of course, you have to cook up something weird to do it nicely. But the very interesting point is that this process allows you to describe the invasion properly. Okay. So yeah, so the main proof of the theorem is based on a comparison principle with suitable things that we derive thanks to this computation here. Okay, how much time do I have? 3 minutes, perfect. So I will just comment very briefly on these 3 minutes on changing the previous model here that I didn't write, but convolution plus KPP, okay, with actually more general J here that can include, I told you before, Levy germs, which are close to something called fractional Laplacians. Okay, so here I extend this thing for fractional Laplace or not. That is, J could be a nice thing as a convolution and a fractional thing like this as a fractional Laplace. Okay, fractional Laplace, it's pretty natural from some stuff in biology because it or in physics because it appears to be quite regularly a macroscopic limit of some process or dynamical system or whatsoever. Okay, and I take into account here an extra phenomena which is called Allee effect, and Allee effect methodology is a thing saying that okay, if your population is too small, it's too small to survive because it doesn't have as many individuals as necessary to survive. An example is given by okay, in English it's surrogates, right? This kind of animals that are like this. So if you have only one surrogate on somewhere, okay, it can be killed by some eagle or something. However, if you have enough surrogates at the same spot, they can all communicate within each other to see if there are some predators, okay, and they will make some sound, and if there is a predator, they will all leave. Okay, so it's a way to like use this thing. If there is only one guy, he's going to die, but if they are in a group, then they can a bit communicate, right? Okay. So let me just quickly comment on what we obtained for this kind of thing, and then I will start. So this is So this is roughly this is some simulations quickly. Oops, sorry. So if I take a fractional Laplace with some exponents, my beta if my beta, sorry, should not be the same, of course. So if my beta is large enough, it should be 5 here. My beta is large enough, then I will kill everyone, and so I will have a linear spreading. However, if it's in such a way that I will show you at this slide later, I can have an acceleration with this phenomena of flattening. Okay. So what was known before the paper with Jérôme that we've been doing is that, okay, first of all, there were results for fractional Laplace only and convolution operators separately. And we have mixed everything with a simple thing. And there were some non-sharp rates that were known from some papers. Okay. So I will stop with this statement. If we assume that beta is smaller than something, okay, S is only the shape of the tail of the J, then my x of t, the point where the solution has value 1/2, let's say, or any lambda, is spreading with exactly the exponent t beta over 2s beta minus 1. So if I can just show you this range of parameters, okay, in this kind of general framework, there is a separatrix between linear spreading and acceleration, and you can cook up independently of the parameters. And I will stop, I think. I will not show you the proofs because it's a bit long, and I will for your attention. Yeah, so this has been a movie about this in Australia. It's a real movie.
Any question or comment?
Mm-hmm. Mm-hmm. Yeah, in a sense, yes. Yeah. And in fact, I could even say that we take, how can I say that? to get the sharp rates, we have to understand how much unstable it is in a sense, because it's a dynamic, it's a bit the dynamic. I mean, what I showed before was that maybe I can actually show, in fact, now, in fact, yes. For example, for the last example I was showing, a way to understand is to solve the ODE that is this ODE, more or less. In fact, it's not exactly this one because we need to change for some technical reasons. But anyways, we really use the ODE and the way that it's close to zero, right? So it's this is really important. Yeah. But the problem afterwards is to know how you couple the ODE with the dispersion motion. This is for the basic models. It's okay, but if you have nonlinearities that are a bit bizarre, it's can. What do you mean? Mm-hmm.
Barrier, right?
Ah, yes. Okay, I understand. Yes, yes. So, okay. So, for example, for this, when you have an equation like that, you have a comparison principle that tells you that if you start between 0 and 1, you stay between 0 and 1. But on top of that, even if I put my famous rho here, it was the integral, since here I have a u, the thing will remain positive. However, it's not going to remain below 1. But positive, yes. That's why, in fact, it was a bit hidden in that picture. I can show you again if I find it. Here. There I put kind of intentionally this kind of wavy behavior because it's not clear and it's not obvious that your solution is monotone and is below 1. In fact, in some cases, it's true for rho, but clearly for n, it's not true. Right? Because it's, for example, in fact, for toads, some people prove that your rho will stay below 1, but since your n is a density, if your rho is close to 1 and you're oriented, you can imagine that your density will have values a bit higher, and you see? So well. But theoretically, for all models, when you have a non-locality, it's not clear that the solution enjoys basic bounds here.
In these models where you have for the tone, you have theta dependent.
Mm-hmm.
So the course to be dependent on theta.
Uh-huh.
But maybe in some sense it becomes not dependent on theta in a very long time. No?
Okay, I can comment on that. So indeed, so for example, here in this case, for France. So for France, so for bounded, let me do it that way. So if this is x, this is theta, for example. Okay, for bounded things, basically at the back, you will be homogeneous. This is what you say. Because when you have invaded, then everybody is here, so nobody has an advantage because they're just in the front. So they don't have advantage for food because they are here. So indeed, at the back, we expect things to be flat. And at the edge, then when you are normalized, the density will start being oriented like that. So the behavior, in fact, what is almost true is that the behavior of the solution at the edge looks like exponential minus lambda star xi, where xi is the translational for the front, q, and q is the repartition of the trait. And actually, at the edge, of course, it's like that, and at the back, you don't have decay because it's flat. So you just have Q, okay? But this Q is a constant, basically.
So we use this kind of canonical because this is for canonical.
So this is canonical for fonts, yes. For fonts, it yes, yes. So I can show you, in fact, roughly. So here it's a bit different because it's for acceleration, but here you cannot read because it's too small. But here, in fact, we have exponential t times, and here we have minus something in x and minus something in theta. So yes, we do it. But since for the acceleration, theta and x are coupled, so it's a bit harder, but still. But for fonts, yes, we often use that. In fact, actually, I didn't mention that, but earlier, before proving, yes, it's in the C also. Before proving this of traveling waves, okay, there's no comparison principle for the equation, but still we use in fact some how is the name again, index theory, index theory, and at some point we need to find the index of a solution for some vector, blah blah, and it's related, and basically we can do it because the and we take exactly yeah, we have to compute the index, and in fact it's very important. Your life is a bit safer because you know that you have some separate thing like that. However, it's up to my knowledge, it's not proved that in fact it would be a further after that, but it's not proved that a traveling wave will attract your solution because it's difficult. It's non-local and there is no comparison, so you need to do things, and it's in fact I started to do it. Not done.
So for this problem, we didn't study the kind of stability.
No, so in fact, yes. So in fact, okay, I can explain a little bit. Yeah, this is much easier. Even okay, it's easier when you have a font-like behavior. But when you have acceleration, it's difficult because you don't have a profile. So if you want to say what's the thing, it's like there is no like separation of variables or something like this. So it's a bit more difficult to say that it's going to be close to something. No, it's not really. It's not done. In fact, there is nothing really. But yeah, in fact, here you see that I have a CT, which is for a font, I have a CT, which is the main speed, and there is a correction here. So, which is due to the fact that, in fact, with the initial data like this, and you want to look like at some point you want to look like a traveling wave, it has to modify, right, to like that. So it takes some more time because this is the speed of that guy, but this one has to resemble, so it's going to lag. Okay, so this is called in the literature Bramson correction. It's lag between this and that when it modifies. So now, what is not known is if you take this frame here, are you going to look like the traveling wave when it is large? Because basically, to do that, people sandwich the solution between two things, and here you can do that. So it's not easy.
people online. Okay, then Emeric, has been a really pleasure to have you here in the department.
Thank you.
For accept the invitation to
Of
give
course.
us this presentation. Be careful with tools.
Thanks a lot.
That's it. That's it.
Thanks. Yeah, I take the opportunity to say thank you for your warm welcome here. I was very happy to stay for a few months in the department, and I'm sure I will come.
Too quickly.
Yeah, so it means that I will come today.
Yes.
Sorry, tell me.
Don't blow up like this here.
If you put crazy nonlinearities, it's